Okay, today we're going to be comparing two proportions using a confidence interval. So my strategy here is that I'm going to kind of take the formulas that we have for looking at the confidence interval for a single proportion and the formula for a single hypothesis with one proportion and use this to figure out what should happen when we're comparing two groups. So just kind of reviewing the general setup of these things. When I'm looking at these confidence intervals, I have my center, p hat, plus or minus my distribution, so z star, times the square root of my p hat, q hat over n. Confidence intervals are based off of samples, and confidence intervals in particular, I start with sample information and it tells me what should happen for a larger population. Hypothesis test, on the other hand, here I have that I'm looking at percentages, normally distributed, center of p, standard deviation square root pq over n. These are based off of population claims, and they tell me what should happen for the likelihood of my sample data. So hypothesis test, these are based off of claims. Both of these setups here use the same base model. I have p hat, so something to do with percentages as my center. They're both using z-scores, and they both have the same kind of standard deviation square root pq over n general setup. So assuming I get the model for comparisons, I should be able to immediately do both confidence intervals and hypothesis test. And I'm going to make the model today, and I'm going to get all the way through this, and I'm going to start my way into that, but I won't quite finish today. So just to make sure I understand how comparisons work, I've set up a couple of inequalities here. I just want to run through them to make sure I understand what I'm looking at. Because if I understand these base inequalities, I'm going to be in great shape for the model later on. So suppose that I'm comparing the win rates for two different roller derby teams. So I have a Seattle team and I have a Portland team. If I take the win rate for Seattle's team and I subtract the win rate for the Portland team and I get a positive number, what does that tell me about the groups? Well, if I just think about adding this to the other side, this tells me that the win rate for Seattle is higher than the win rate for Portland. Just as a reminder of how positive and negative numbers work, if I have a large number minus a small number, I end up with a positive. Like 6 minus 2 gives me a positive 4. So I have my large and I have my smaller. Large and small being relative to each other. These could both be really small numbers. So this could be a win rate of 3%. This could be a win rate of 2.9%. It's still larger. Let's suppose I do the comparison Seattle minus Portland, and this time I get a negative number. Well, again, I can get rid of this subtraction by adding this to the other side. Inequality stays the same. So this would tell me that Seattle did worse than Portland. So if it's greater than 0 when I do the subtraction, Seattle's better. If it's less than 0, Seattle's worse. What do you think happens if it's equal to 0? Well, let's do the same thing. Let's move the symbol over. When I add the probability of Portland to the other side, I get that the win rate for Seattle is equal to the win rate of Portland. If you look at these, you'll notice I have every possible comparison that could come up. I have Seattle doing better, I have Seattle doing worse, and I have Seattle doing just as well as Portland, but no better. And I did this by doing subtraction and then looking at the sign, seeing if it was positive, negative, or contained 0. So my note here is to compare two percentages, first percentage and second percentage, I can subtract the values and examine the sign. So previously, I just needed to understand the model for p hat, or for a single p. This time, it really feels like I need to understand what's going on to compare the differences of two sample win rates. So this is what I'm aiming for. I'm going to try to come up with a model for this thing. I'm going to turn the page and I'm going to see what we can come up with. Okay. My model for a single proportion is p hat. I'm using the subscripts of 1 to represent the first group because I have the same model and setup for my second group. And my goal at the end of the problem, I'm jumping ahead a little bit, is I want to figure out how do I take these two models for the first group and the second group, and how do I combine these things? I'm going to fix my camera so you can see me a little better. How do I combine these things to get a model for both of those groups together? Well, let's do a couple of scenarios and see what happens. I'm going to just do a quick what if. So suppose I expect the win rate for the first group to be 5%. And suppose I expect the second win rate to be, say, 3%. This is just a made-up example here. What do you think my win rate should be when I'm looking at the first group, take away the second group? Well, I expected it to be 5 for the first. I expected it to be 3 for the second. So I expect the difference between these groups, that's what the subtraction does. It tells me the difference. I expect the difference between them to be 2%. And how did I get that? Well, I literally just took these two numbers and I subtracted them. So if I want to know what the center should be, well, I'll still have a normal distribution, but I'm going to take whatever my first percentage is, and I'm going to subtract whatever my second percentage is. So here I have the name of my model. It tells me I'm going to be comparing two percentages. This n reminds me that I'm dealing with a normal distribution, so I'm going to be using z-scores when the time comes up. And this component right here is telling me I should have a center of p1 minus p2. If I cover up everything with the 2 there, you'll notice that this still looks just like p hat is normally distributed with the center of p. In fact, my standard deviation is going to look really familiar as well. I'm going to have pq over n. So there I literally have my old model. P hat is normally distributed with the center of p, and a standard deviation is square root of pq over n. Now I have two groups, so I'm going to have the same spread setup for my second group. Now, I'm wondering what symbol I should have here. I'm going to put the symbol down and I'm going to kind of explain where this is coming from. When I have a first group and I add a second group, I actually end up adding the spread between them. If you're wondering where that comes from, when I'm taking the standard deviation of the first group and I combine the standard deviation for the second group, it's really like having two independent groups that are going in two different directions. So suppose that group 1 goes in this direction and group 2 goes in this direction. So they're entirely different or independent directions. So this statement is only true if the first and second group do not affect each other. While for triangles, that tells me that these things go at 90 degrees. If I want to find what it looks like when they're together, well, the difference of the two groups is the spot that joins the two separate spots. So I'm going to have a relationship for this first side of the triangle and the second side of the triangle and the hypotenuse. And if you know the Pythagorean theorem for triangles, this tells me that the standard deviation for the first group squared plus the standard deviation for the second group squared is the standard deviation of the combination squared. In order to get rid of this square, I have to take a square root. So my standard deviation ends up being the square root of the first variance plus the second variance. I went through that a little bit quickly. I recognize that. I don't necessarily need to spend too much time worrying about rederiving this, but I need to just make sure I understand roughly what it's telling me. So let's lean into that a little bit. Notice if I cover everything with a 2 up, I'm left with p hat is normally distributed with the center of p and a standard deviation of square root pq over n. I have my old model for the first group. I'm going to do the same thing now where I cover up everything with a 1. P hat is normally distributed with the center of p and a standard deviation of the square root of pq over n. So I've really taken my two group models and I've combined them here into one larger model that will compare the difference of the groups. It's a little strange when you start out with, but as you practice this, it will become first nature. So let's start that process of practicing and going over assumptions. So print it all nicely so you can see it. This is my model. I'm just going to label things again. This tells me that I'm going to be looking at the difference of two groups. And I'm going to be comparing the percentages. So maybe Rotten Tomatoes score for two different movies, two different percentages. This is my center, and it's really the difference of my two centers. This is my standard deviation. When I combine groups, I add the spread. The more variables I have, the more I am adding underneath that standard deviation. I'm going to use this same model next time, so I'm just writing myself a note. This is my model for my hypothesis test. So I'm already halfway done for this next lesson because I will have the 4 steps as always. I will state my hypotheses. I'll have my model. This is my model. I will calculate my p-value, and then I'll have my conclusion. Today, I'm creating confidence intervals. And a reminder, confidence intervals are based off of samples. And the formula is always going to look like my center plus or minus my critical value, or my distribution star, multiplied by my standard deviation-like thing. I call that the standard error. I'm going to match things up. So looking above, my center was P1 minus P2. I want to say the sample version of that. Well, the sample way of saying P is P hat, so I have P hat 1, minus the sample way of saying P2 is P hat 2. Second part of this, my distribution. I'm working with the normal distribution still, so I'm going to be working with z-scores. I know that z star for 90% is 1.645, for 95% it's 1.96, and for 99% it's 2.576. Those values are still true. Finally, for this last piece, I'm going to take my standard deviation and I'm going to rewrite that, but based off of the sample. So I'm pretty much hatifying it. Everything that was based off of the population before, I make it based off of the sample just by adding hats. Pausing here. This should look familiar. P hat plus or minus C star square root P hat Q hat over N. That was my formula for a confidence interval for just one group. And now I'm going to repeat it again. So I have the same stuff, but for my second group. So in your head, you should get in that habit of thinking, this is really just one group, but I'm doing it twice. So my assumptions, well, the same big three that I always have. I need to have a random sample. By that, I mean there should be no bias in the way I've collected the data. I should have independence between trials. So independence within my sample sets. That's hard for me to judge. So luckily I have the backup for that. I have the 10% rule. And lastly, I have large N. Large N was I wanted to have at least 10 successes and at least 10 failures. But I need 10 successes and 10 failures for the first group, and I also need 10 successes and 10 failures for the second group. So if you're wondering, well, which group needs to be random? Which group do I need independence? I need this for both groups. Because I'm essentially doing this confidence interval twice. I need it to match up for both. And finally, I have one last assumption here. I need to make sure that group one, there's no cheating within group one. I need to make sure there's no cheating within group two. My random and independence within those groups takes care of that. But I also need to make sure that group one isn't intentionally ruining group two's result. I can't have cross contamination there. So as a final assumption, besides just independence within, I need to have independence between groups to make sure that the two groups are not affecting each other. If you're looking at this and you're starting to get nervous and you're thinking, this looks like a whole lot of calculations, but let's just try it out and see what this looks like in practice when we're really going through a problem. So let's create a 90% confidence interval for the difference of two groups. If the first group has 18 successes and 25 trials, and the second group has 22 successes and 50 trials. I'm going to just do a little bit of scratch work on the side. I'd recommend you do scratch work on the side too. And I'm going to figure out my first success rate, second success rate, number of trials, second success rate, second failure rate, number of trials. First group, I had 18 successes out of 25 trials. I had a 72% success rate. If that first group won 72% of the time, the failure rate there was 28% of the time. Number of trials, I had 25. I'm looking at a 90% confidence interval. If I want to be 90% sure, I need to use a critical value of 1.645. P hat for the second group. Well, I had 22 successes for the second group out of 50 trials. I'm just going to write down my N. I saw that right there. 22 out of 50 trials. And that gives me 0.44. If I have a 44% success rate, then for the second group, I have a failure rate of 56%. Just as a note, I don't know how this data was collected. I don't know if I have independence within. I don't know if I have independence between. It doesn't give me enough information. But I actually do know that I don't pass the large N assumption for this. Do you see how I have 18 successes for the first group out of 25? This would mean that the number of failures that I have for this first group is 7. So I might have enough successes at 18, but I actually don't have enough failures. So this is just a word of warning. I really should stop. But I'm just going to be a little bit of a rebel, and I'm just going to keep going. A rebel in like the most minor sense of the word possible. I'm doing a math problem and I shouldn't. I have p hat for the first group minus p hat for the second group, plus or minus c star. And then I have a big square root. When I make large square roots, I usually start the thing off. I write in everything on the inside. And then I close my big square root. My first success rate was 72. My second success rate was 44. So already I can see that it looks like there's going to be a difference between the groups of about 28. In particular, it looks like group 1 is going to be bigger than group 2 by 28%. At least this is the way it was for the sample. Now, sometimes I might see a larger difference, and sometimes I might see a smaller difference. So I need to see how that varies, and the margin of error, this next piece is going to tell me what that looks like. So my z star is 1.645 times the square root of p hat and q hat for the first group over the n for the first group. Do you see how I have the confidence interval here using all of my first group information? First success rate, first failure rate, number of trials. I'm going to do the same thing for the second group, and it just adds to the spread. So I have second success rate, second failure rate over the number of trials for the second group. I'm going to take a moment here to type this into the calculator. I'm going to ask that you do the same. I'm trying to get the entire margin of error. So if you're watching this at home, maybe pause that video and then see what you get. And I got a MO of 18.8%. That's a considerable amount of variation. When I do the addition and subtraction here, I get a low value of 0.092, and I get a high value of 0.468. Now, this doesn't mean that the first win rate is 9% and the second win rate is 46%. In fact, I can see up here that my success rate, it looks like 72% or it looks like 44%. So this interval here is really telling me how far I expect these numbers to be different. This is a confidence interval for the difference of the two groups. So which group is bigger? Well, let's look at the signs of the numbers. 9.2%, is that positive or negative? What about 46.8%? Is that positive or negative? You may have noticed your confidence interval for P1 minus P2, both of these numbers here were greater than 0. So I saw that because my low value of 9%, that's a positive number. My high value of 46.8%, that's a positive number. So I have my confidence interval for P1 minus P2 is bigger than 0. I'm going to move this P2 to the other side, and let's see what we end up with. P1, I'm adding that over. P1 is bigger than P2. I can see that up here as well, so that's kind of tracking. My P1 looks bigger than my P2. So the question might be, how much bigger? Well, that's exactly what this confidence interval here is telling me. I would say we are 90% confident. We made a 90% confidence interval. That the interval, or the difference in success rates, for group 1 is bigger than group 2 by anywhere from, on the low end, 9.2% bigger, to on the high end, something like 46.8% bigger. So the trick here is when I'm looking at these differences, I'm thinking of them as subtractions. I'm thinking of them as being either positive numbers, negative numbers, or including 0. In fact, the computations are so similar to before that the biggest difference is this conclusion step. So I'm going to turn the page, and we're just going to look at a whole bunch of conclusions together. Example 9 is a great one to kind of practice on your own. I'm going to put a star by that. Try this one out. This should be within your locus of control. And we're just going to look at the conclusions for these 3 things down here at the bottom. So let's suppose I created a confidence interval for Seattle minus Portland, and I got a low value of -4%, and I got a high value of -3%. Are these positive numbers or are these negative numbers? Well, this is a negative. That's less than 0. So ultimately, I'm just wondering, are these things bigger than 0 or less than 0? That's what I'm doing for these comparisons. This is a -3%. That is also less than 0. So this tells me that my Seattle minus Portland interval, both of these things are less than 0. To get rid of subtraction, I add this to the other side. So I'm going to add that Portland symbol to that side. This tells me that Seattle did worse than Portland by, and the amount that it's by are going to be the numbers above. So we are 95% confident that the percent for Seattle is anywhere from 3% to 4% lower than Portland. You may have noticed that I switched those numbers and I did 3% to 4%. If you would have said is anywhere from 4% to 3% lower, that would still make sense. I hope you're seeing, though, that that negative number is really encompassed in that word lower. If that was positive, I would say 3 to 4% higher. The signs are determining sort of what word I have there in my conclusion. Let's look at another one. Seattle minus Portland, -4. I'm just looking at the signs, that's less than 0. And positive, oh no. So previously, I've just had intervals where they've both been negative or where they've both been positive. I've not had one of these half and half things going on. And what's happening here is, note, 0 is inside our interval. If it's everything from -4% all the way up to 10%, that includes 0 in between those numbers somewhere. And why is 0 a big deal? Well, this means I could have Seattle minus Portland equaling 0. So whenever you have an interval that goes negative to positive like this, it's telling you that you could have equality there somewhere in the interval. I'm going to move this symbol to the other side. This means it's possible that Seattle is just as good as Portland. Now, if you wanted to go into this in a bit more detail, this here, this negative number is saying that Portland could be better by up to 4%. This positive number is telling me that Seattle could be better by up to 10%. So I really run the full gamut there with either of these cities being the better city. As a result, when I have 0 inside of my interval, I say my results are inconclusive. I cannot determine who the better team is or who the better city is. Let's see what happens if I try to switch the order up here. So suppose I created a 95% confidence interval for Seattle minus Portland, and I got -4 to -3. That's exactly what I have up here. I have Seattle minus Portland, -4 to -3. So the question is, what's this going to look like if I try to do Portland minus Seattle? And I just want to remind you of how subtraction works. So this is just a little bit of scratch reminder. If I do 5 minus 2, I get 3. But if I do 2 minus 5, I get -3. So if I switch the order of subtraction, I change the sign. So if I take my interval of Seattle minus Portland of -4 to -3, and I switch the order to Portland minus Seattle, I'm going to have the same numbers, but I'm going to change the signs. So I'm going to have a positive and a positive. Notice here, these are positive numbers. So this tells me Portland minus Seattle is bigger than 0. This tells me the Portland group is better than the Seattle group. If I'm looking over here, I have Seattle minus Portland is less than 0. These are negative numbers. This tells me that Seattle is less than Portland. And if you're thinking, well, why am I getting two different answers? I want you to really look at this. You're not getting two answers. It's the same thing two different ways for language, but it's the same end result. Saying Seattle is worse than Portland is identical to saying Portland is better than Seattle. So my suggestion to you is when you're setting up these problems, if you have the option of doing large minus small and getting positive numbers, or small minus large and getting negative numbers, let's try to keep things positive and using this first setup, because that way we have less negatives to worry about when we're going through the problem. We're less likely to make a sign error. Let's do one more example here, and then I'm going to leave a lot of this packet for you to go through on your own as more problems for you to practice and internalize. So let's look at example 9. So this was a problem that I said you should be able to do on your own. I want to give you a chance to do that. So go ahead and pause this video, take a minute, see what you can do. Okay. Mr. Wary performs a random study of PCC students and finds that out of 200 students under the age of 20, 120 of them played Pokemon Go. So I'm going to have my under 20 group, and I'm just going to list everything as it comes up. So it looks like the success rate for this first group was 120 out of 200. 120 out of 200 is 60% of this group has played Pokemon Go. So for failure rate, 40% have not played Pokemon Go. And this is out of 200 players. In contrast, out of 100 students 20 or older, so this is my 20 plus group, and it's out of 100, so my second group is out of 100. My success rate for my second group was 40 out of 100. As a decimal, that's 0.40 or 40%. My failure rate, 1 minus this, is 60%. They asked me to create a 95% confidence interval. I know for 95%, I'm dealing with a critical value of 1.96, or if I'm feeling lazy, I might use 2 from the 68, 95, 99.7. Now, before I create the interval, I'm going to talk about the assumptions. First, it says I did a random study for both of these things, so I passed random. Second, one person playing Pokemon Go might affect another person playing Pokemon Go, but 200 and 100 people in these age groups is well under 10% of all people in those age groups. So I'm good for independence based off the 10% rule. I have one group in the under 20 shouldn't affect someone in the over 20 group. And finally, I have at least 10 people in each group that play and do not play Pokemon Go. So I passed my assumptions. I'm going to make my interval. And I have 60% for the success rate for the under 20 group. So I'm going to do confidence interval for P1 minus P2 here in this order, because 60 minus the 40 will give me a positive 20. So if I do it this way, I should end up with positive numbers. If these values were switched, I might want to create a confidence interval for P2 minus P1, do this in the other order. It doesn't really matter where I end up, I just have to be really careful that I write down the setup somewhere. All right, so I'm thinking I have my formula for a confidence interval for a single group, my under 20 group. So if I was just creating the confidence interval for my under 20 individuals, it would look something like this. And now I'm going to do the same thing for my second group, my 20 and older. So I subtract the center, I add the spread. So my confidence interval for the second group, I had center 40, I had a z-star, shared z-star of 1.96. I add my spread, I had 40 as the success rate, 60 as the failure rate out of 100 trials. I'm going to type this into a calculator and I'll get a low value and a high value. I'll ask that you do the same. When I type this into my calculator, I'm going to show you a little bit of a trick. So I'm typing in 0.6 minus 0.4 minus 1.96. I find that I don't have to go crazy with parentheses here. Order of operations keeps a lot of these things in place for me, so I really just need a start and ending parenthesis for the square root. On my TI-84, it keeps everything underneath the square root for me, so I didn't even need to type in those parentheses. But there'd be one at the start and one at the end. I'm going to hit enter. I did this with the minus here, so this is my low value is 8.24%. Okay, here's my calculator trick for you. If I hit the second button and then 0, it's going to pull in the last entry that I typed in. So I'm going to hit second and enter, and I have the last thing I typed in, and I'm going to change this minus to a plus sign. And I'm changing that symbol immediately before the 1.96, because I'm changing the thing before the plus or the minus. So on my packet here, my high value was 31.76. When I'm looking at these results here, I'm noticing that this is bigger than 0, it's a positive number, and this is bigger than the 0. So when I'm comparing the two things, I've done my under 20 group, minus my over 20 group, and I got that that was greater than 0. Moving this symbol to the other side, this tells me that the under 20 group plays Pokemon Go more than the 20 and over group. How much more? Well, I'm 95% confident that my under 20s play anywhere from 8.24% to 31.76% more than my 20 and older group. So I compare the two values by looking at their signs, positive, negative, or 0. If it ended up that there was no discernible difference between the two groups, I would have noticed that this would be a negative and this would be a positive. Whenever you have two different signs, that's when you know your results are inconclusive. You have 2 more pages of stuff in this packet if you're looking at lesson 4. These are more problems for you to go through and practice on your own, or start doing the homework and see how you do. This is it for lesson 4 for now. I'll look forward to doing more math with you later.